Okay, so let's use our templates to take some notes on two-dimensional interference patterns. So I'm going to start here just with the single diffraction. So what could have created that? Well, if I create a boundary here and a boundary there and leave a little opening, okay, boom, there we go, right? That if I had straight waves coming in here into my boundary, and then they diffract it. Now, they wouldn't diffract all the way back to the boundary, right? Like, this would actually be a cone that would look something like that for realism. But just for sake of argument, let's say this is the diffraction I get. Remember, that's identical to just tapping here, right? So if I tap, 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 tap there. So a couple of things about the anatomy of what we're looking at. I've got each of these lines represents a wavefront of crests, right? So that the distance between each successive dark line is exactly one wavelength. Now, just so we can see what it looks like, that means that there's a line of troughs directly in between the line of crests, because we know a crest is separated from a trough by exactly 1/2 of a wavelength. And I could draw in all of those lines or wavefronts of troughs if I want to. It just, the picture would get just terribly cluttered if I did that. So what we're just notice here is in between each line of crests is a line of troughs. So that's what we have. So let's go on to now this, which is pretty much what our simulation looked like after we let it play for a while. I'm just going to call this S1 and this S2 for source 1, source 2. Let me actually switch to a different color because that's not coming in that dark. S1 and S2, right? The distance between the sources we call D. Now remember, this could be just sources tapping here, or this could be the same thing as if I have created a double slit diffraction, okay? All right, so let's do the same sort of analysis that we did before, where we're looking at, can we identify where our nodal lines and antinodal lines are? Well, here we go. I think we can see that we have an antinodal line here, right? This place where all the crests are overlapping crests and troughs overlapping troughs. So I'm just going to pick one point here. I'm going to call that point A and talk about what we talked about before, the idea of path difference. So from source 1, oh, that's a little off the screen there. So from source 1 to point A, how far is that? Well, 1 wavelength, 2 wavelengths, 3 wavelengths, 4 wavelengths, 5 wavelengths. Okay? From source 2 to point A, 1, 2, 3, 4, 5. This is what we were talking about before. And so I can then say the path difference to point A would be the absolute value of the length of path 1 minus the length of path 2, which in this case would give 0. And if I did that at any point along here, let's say if I did point B and did the same thing, that'd be 1, 2, 3, 4, 5, 6, 7.5 waves. So to point B from source 1 to B is 7.5 wavelengths. 1, 2, 3, 4, 5, 6, 7.5. And from source 2 to B is also 7.5 wavelengths. And notice the path difference for every point along that line is exactly 0 wavelengths. And so that's why this is the principal antinodal line. It is a line along which the path difference is always exactly 0 wavelengths. So then the first antinodal line, or the first order antinodal line, is going to be a line along which the path difference is exactly 1 wavelength. And we can pick, say, this point here and count it out. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6. 7 wavelengths, 6 wavelengths. Path difference is 1 lambda. So I'm going to draw in that line. There we go. Notice that's like curve I was talking about before. I'll talk about that a little bit later. Path difference there is 1 wavelength. Now this is why, folks, we have both of these are called the A1 line because the condition to them is the same, that the path difference is exactly half a wavelength. Well, where does that come from? Why is it exactly identical? And it comes from this absolute value here. Because for this line, the distance from source 2 to source 1 is 1 wavelength bigger. And to this one, it's from source 1 to that point rather than the source 2 to the point. That's 1 wavelength bigger. And since both have the same condition, there's no need to name them differently. And just to put this out there, I can draw in, whoops, I got a little crazy at the end. The A2 line, path difference is 2 wavelengths, and I can then draw in the A2 line over here, path difference is 2 wavelengths. The reason why it gets a little curved is I tried to make these exactly equal, but Microsoft Word is only so good at that, right? And here's my A3, and there's my A3 line. Path difference would be 3 wavelengths. Path difference would be 3 wavelengths, and you can count that out yourself if you're a doubting person. So then, where are my nodal lines? Well, that's points like here, where if you notice I'm on the crest coming from source 1, but from source 2, I'm in the trough. I'm in between these two crests here. And so from here, it's 1, 2, 3 wavelengths. Here it's 1, 2, 3.5 wavelengths. So the path difference all to these points here is exactly, path difference is equal to half a wavelength. But if we start looking at this line here, and I pick a point, let's say we pick this point here, 1, 2, 3, 4, 5 wavelengths, 1, 2, 3, 4, 5, 6.5. The path difference is 1.5 wavelengths or 3/2 wavelengths. And that's always true on the n equals 2 line. So the n equals 2 line has a path difference of 3/2 wavelength. And if you see the pattern going on there, this is the n equals 3, and the path difference there is going to be 5/2 of a wavelength. And that's always the pattern. And I can obviously do the symmetrical points over on this side. So N1, N2, N3. The conditions for any N3 line is going to be the path difference is 5/2 of a wavelength. So what seems to be happening here? Well, if I take the path difference, which is just the absolute value of L1 and L minus L2, where L1 is the length from the source in question out to the point, minus the length from the source in question out to the point, that's going to always equal some multiple times the wavelength. If n equals an integer, I get constructive interference, and if n equals a half integer, I'm getting destructive interference. So what happens if it's not an integer or a half integer, if it's somewhere in between? Well, that's why this is really complete constructive and this is complete destructive. So if I'm closer to the integer, say like n came out to be 1.04 rather than 1, it's probably constructive, just not complete constructive. And if it came out to be like, I don't know, 2.58, it's closer to the destructive than it is to the constructive. And so there are ranges between constructive and destructive there, but we're really only be concerned with the complete constructive and the complete destructive interference. But that's the underlying architecture of what's going on there. So the reason why we have these curves is, let me just draw you something here. Actually, no, we'll do that a little bit later. What I wanted to show you is our picture here. Notice it's the same wavefronts, but all I've done here is D is smaller. And so you can see my antinodal lines. Let's draw in our A0. And oh, here's the A1. And here is the A1 as well. So they're much further separated from one another. So why is it that decreasing D made the separation between antinodal lines greater, or nodal lines greater. It's the same difference. Well, if you notice here, it's just very simply, when the sources are closer together, there are fewer points of overlap of crests. We know we get constructive interference when our crests overlap, so if they're just overlapping fewer times because of the geometry, I'm going to get fewer antinodal lines. Just as simple as that. And that's the reason. The other pattern we tried and looked at is what happens. So D is the same as it was before, but now if you notice, here the wavelength is longer. So with a larger wavelength, let's draw in our antinodal lines. There's our A0. Here's our A1 and our A1 as well. Not perfect there, but there you go. With a larger wavelength, the antinodal lines and the nodal lines, same difference, are further apart. And of course, I'm referencing that to here, which has the same, if you notice, they have the same D, but here the wavelength is smaller, so with a larger wavelength, everything's further apart. Why is this the case? Well, with the larger wavelengths, once again, there are fewer places of overlap, right? And so what determines the spacing between the antinodal lines is how often in space are crests overlapping crests. When the sources are far apart and when the waves are compact, there's more wave fronts, it kind of just makes sense that they're going to overlap more times. So hopefully that's a sufficient explanation to why our patterns are happening the way we said they were. And hopefully that helps us understand how to identify what the name of the antinodal line or nodal line is by counting path differences. So one last thing that I wanted to talk about here. So once again, we call these lines, they're not really lines. What are they then? Well, it kind of helps to look at this picture not just in terms of 2 points going in one direction, but if I had these and they were spreading out in all directions, right? Our two circular waves spreading out in all directions, we would get a very different looking pattern. So this would get messy really quickly, but I just kind of want to show what we would get. We would get an antinodal line that would do this, right down the center between the two. And we saw that the next antinodal line was kind of like going out like this and going out like this, and the next one was going out like this and starting to curve a little bit there. So if I just were to continue this pattern, I would get that. Okay, so these antinodal lines, which look straight in a certain perspective, are actually curves. Now you may be looking at this and going like, oh my God, I know what this is, I know what this is. And if you said that these are all hyperbolas, you're correct. Because what is a hyperbola? Well, it's we have 2 points for a hyperbola that are called focus points, right? And what it is it is a locus of points such that the difference between those two lines has some sort of relationship, which kind of makes sense because we define path difference as L1 minus L2, and that's very similar to the way that a hyperbola is derived. Now you'll remember an ellipse had 2 focal points as well, but that was the locus of points such that the L1 plus L2 was equal to the same number. And so that's really the difference between a hyperbola and an ellipse. So these lines, antinodal lines, are really a family of antinodal hyperbolas. And that's really what's going on here, except that we're only looking at them in the short term, and any curve in a short amount of its segment looks like a line. You may have learned that term from math called local linearity. Now, For anyone who's freaking out about all the hyperbola stuff that I was just talking about, you can literally ignore it and just assume that these are lines. I just wanted to bring it up because it's true and it's reality and it connects to what many of you are doing in your math classes, but that's not something that we're going to focus here on in physics.